All right, time to continue the discussion about atoms and ionic bonds from Chapter 3. We need to move further on our learning objectives to use electron configurations, valence electron configurations, to generalize the chemistry of each family of elements studied in the chapter, and look into the alkali metals and alkaline earth metals and how they have various kinds of reactions we can generalize with hydrogen, oxygen, water, and ammonia, and halogens. The first group of compounds or elements we need to talk about are the alkali metals, the group 1A elements, which are all on the left side of the periodic table. They start with lithium, progress down the chart to sodium, potassium, rubidium, cesium. Francium is very unusual, so we're not likely to actually encounter any specific examples with it. They are indeed metals, which give some of the characteristics that we commonly think about, being metallic, bright, silvery, shiny things. Malleable, meaning you can pound them into sheets, and relatively soft. You can cut them with a dull spatula or dull blade. They are metals, so they conduct electricity. They are very reactive, and that's one of their features of note. And because of that, they only occur in salts, namely it's hard to get them in a pure form. They are known as reducing agents. Now this is a topic that we're going to come back to with time, but for the moment let's describe it as what? Well, reducing agents are things that give up electrons easily. And we can make sense of that, in fact, already based on the data we've looked at from this chapter. In other words, if we're thinking about ionization energy, they lose an electron easily, as opposed to other elements across the periodic table. The group 1 elements have low ionization energies. The values here are in the neighborhood of 300 to 500. Not that you actually have to know the numbers, but those are relatively low. The reactions that are important with alkali metals include things with halogens, the group 7A elements. The metal will react with a halogen, which, by the way, in case you weren't quite sure, halogens are given this symbol X, and they always occur in pairs. So they'll be shown as X2. And then when they react with a metal in group 1, they're going to make what we call halides. MX is a metal halide because they're going to be fluoride, chloride, bromide, iodide kinds of names. And those metal halides with group 1 elements are very simple looking. Things like sodium will react with chlorine to make sodium chloride, and various other possible combinations of each of those elements from each of the groups. The thing that's worth noting, however, is that some of these group 1 elements are more reactive than others. And so the reactivity order is such that the most reactive is at the bottom of the column, and that would be cesium. So cesium would be something pretty wicked to work with if you had occasion to be using it somewhere. All right. Now, there are also reactions with oxygen, and there are a variety of possible products that can result with oxygen, depending on which of the group 1 elements you're looking at. The reaction of lithium with oxygen is fairly simple looking because you make a lithium oxide, as you might predict from the charges of the typical charge for lithium and its typical charge for oxygen, and it would be a lithium oxide, Li2O. And when you look at the formula, that reflects the idea that lithium should be +1, and the oxygen oxide ion is typically -2. But the more reactive sodium is going to make a slightly different compound when reacting with oxygen. This is oxygen gas now. And so in this case, we have sodium, and there's 2 of them, but the charge on sodium is going to be still +1. But the charge is now something different because we've got 2 of those with the peroxide anion. The peroxide anion has a charge that's apparently sufficient to add up to 2 sodium ions, and so that would be a -2 peroxide anion. Potassium, one more down the row, or down the column, sorry, can't say the names carefully. Potassium reacts with oxygen in a third possible way. And potassium still has a +1 charge, but here it's going to be combining with 2 oxide, 2 O2 and a neutral charge. And so this is superoxide with a minus 1 charge. So peroxide is, I should restate that, is O2 with a 2 minus charge, and superoxide is O2 with a single minus charge. So the differences in reactivities as you go down the column give you different kinds of products. Again, knowing the polyatomic ions helps us to describe these different choices. They might be a lot less easy for you to remember than other things, but it's on that list that we would like you to focus on before you prepare for the next exam. So the superoxide is what you get with the most reactive, the regular oxide with the least reactive of this set of choices. The products that result turn out to be solids. Then there's reactions with water. Perhaps you might have seen this kind of reaction demonstrated in class. Lithium reacts vigorously with bubbling if you just stick a little bit into the water. Sodium reacts violently enough to make a flame. And the typical sodium flame test color is shown there. And potassium reacts nearly explosively. It's pretty wicked stuff. I've seen it used, and it's kind of something you need to do with sufficient safety precautions. What's happening in these cases, the simple solid, the metal, which is not easily obtained pure, but can be, is reacting with water to make metal cations and then hydroxide ions. You can demonstrate that in the reaction container by putting in an indicator that suggests the acid-base characteristic, and that makes for a basic solution. The basic solution detected by something like phenolphthalein or other possible indicators. And in addition to that, the exciting part of that is the hydrogen gas that results. So the hydrogen gas is going to be what will light on fire with the heat released from these reactions. So then, to put this in the context of how we look at this on the periodic table, as the metals in group 1 lose an electron, they're going to form different compounds. When they react with oxygen, they're going to be sometimes charged as +2 ions with, +1 ions, the way they normally are, with 1 oxygen to make an oxide, and that would be a -2 charge. But the increasing reactivities as you go from lithium to sodium, potassium, rubidium, cesium down the column means that different kinds of products can result. Now, why is this? Remembering that the valence electron configuration for each of the group 1 elements, in other words, everything besides hydrogen that would be the first member of that column, the shell number is going to be at least 2, and that 1 outer shell electron is the electron that is lost when the alkali metal ionizes in various kinds of reactions. So if you reacted with water, whoops, let me move that there for you. When you react with water, you're going to make a metal hydroxide and the hydrogen gas that results in very explosive reactions. Now, another curious reaction with the alkali metals, and not one that you're going to run into often, but it's commonly described as an interesting aspect of these elements, is the reaction with ammonia. Ammonia is NH3. So ammonia is a very strong base, and when it reacts with metal from group 1, you get the metal cations. You get this funny ion called the amide ion that we haven't had any reason to label or name so far, but it has a name, the amide ion. Don't panic, I'm not going to test you on it. It has a name, and resulting also in hydrogen gas being formed. Again, a common characteristic from these things is hydrogen gas, isn't it? And so with each of the metals from group 1, these reducing agents that give up electrons easily, lose electrons easily. We'll come back to that idea in another chapter, but they will give up their electrons to the ammonia and result in making the amide ion, and then the hydrogens are released as hydrogen gas. The color shown in this 3-sided flask in the photo represents what you see in that possible reaction. The blue color has to do with electrons being solvated in the solvent. Interesting. Curious reaction to look at, indeed. Now, let's see whether we can do a couple examples with this and make some sense of what these things would be if we expected them to react. Well, let's do the first one with water. So we're expecting hydroxides to form, And so cesium as an ion is going to be cesium +1, and hydroxide is going to be -1, and then some other product was going to result. Well, what other product was it that would result? Think again, if you recall, and that means that we hopefully would imagine there's going to be some hydrogen gas created. Now, we haven't discussed balancing equations, but let's try this one out for size and see if we can make some sense of it. This would be an aqueous compound. And in order for this to come out even, we've got to put in some more atoms left and right. We won't create or destroy matter in representing chemical reactions, so we need to put in more atoms on the left side for everything on the right side, and correspondingly to make sure they add up correctly. All right, so on the left side, we better have to have more hydrogens because there's 3 on the right. So double this one here, and that'll give us a better chance of making it come out even. In which case, we can think of there being now a total of 4 hydrogens here. But in order to have 4 on the right, we better have to put something else and 2 oxygens. Yeah, 4 hydrogens, 2 oxygens. That means there needs to be a second OH group with the cesium hydroxide, and you need to have 2 on the cesium to make that come out even as well. So the cesium hydroxide is aqueous, and the hydrogen gas is also evolved. You could write this equivalently or similarly as 2 cesium ions with a plus charge that are aqueous, and 2 hydroxide ions that are aqueous, and H2 gas. Sometimes one method is more suited than the other, but those are both reflecting the products of the cesium ion and the hydrogen gas and the hydroxide. Okay, so what about rubidium with oxygen? Rubidium and oxygen, well, which elements are the most reactive? The top or the bottom of the column? This one is quite reactive. And so like potassium, we're going to expect it to make the more reactive product, the superoxide. The superoxide, we have to think about that for a minute. And so the superoxide is going to be potassium with O2. In other words, superoxide is the O2 ion with a single minus charge. And in order for this to come out even, what is missing? Nothing more. It turns out that that's all that it takes. So all of the atoms left and right add up, and that would be, rubidium. Get the right element. Oops. Rubidium superoxide. And that would be enough for that reaction. The last one would be the potassium and ammonia. So potassium is going to give up electrons to make a potassium ion, and it will be aqueous because we're, well, in this solution. And but more correctly, this would be described as in solution. It's not necessarily in water here, so we'll say it's in solution. And it's going to give up its electrons to the ammonia and allow it to form this NH2 ion called amide. And then there's also going to be hydrogen gas formed. So I'm going to say we're looking at products formed in these reactions. We could balance the reactions in thinking ahead to how that's going to have to happen in the future. When you do that, you'll have to result in what? You have to have enough of all the parts, or something isn't going to come out even. In order for all there to be that many hydrogens on the right, we're going to have more of the hydrogens on the left. So we'll put a 2 in front of ammonia, 2 in front of potassium, and 2 potassium ions are going to give up 2 electrons to make 2 hydride ions, and then H2 gas also results. Doing this more carefully, this should be noted as in solution, and this would have probably been also in a different form on the ammonia side, but let's not worry about that for now. So it gives you the right idea that hydrogen gas will be evolved from this type of reaction. Okay, I reconsidered. I wanted to give you one more set of examples, and we need to think about the charges on the oxygen-containing anions here, and the lithium with 2 lithiums and 1 oxygen. Well, if you've got 1 oxygen and 2 lithiums, lithiums are going to be the same thing. So the lithium is +1 every time, but 2 of them. So it's going to have to go with oxygen as a 2- ion. In other words, it's oxide. All right? And then if there's K2O2 and CSO2. So K2O2 and CSO2, we got to think about what those are going to be. K2O2, we've already looked at it, but let's see if we can remember what it's called. Here we have 2 potassium ions, and the ion that goes with it has to have 2 negative charge. So it's an oxygen with a 2 minus. It has a name. Think really hard, see if we can remember what it's called. And yes, of course, these take practice. It does for everyone, including me. And this is called the peroxide anion. And then the one in the last example, this would be cesium with oxygen. And there's 1 cesium, and a cesium in this case is going to be a +1. They all are. And it's with the O2 minus, single minus anion. And so that would be the third option. This would be the superoxide. If you've got 1 cesium and O2 has got to be a balancing out the charge, it better be the superoxide with a single minus charge. Okay, enough of the discussion of reactions for alkali metals.